Hello and welcome back to Aerospace and Mechanical Lab 2. Today we are going to talk about our first numerical lab. In this lab we will discuss computational mechanics and we will talk about a structure analysis, what it is, and we will talk about different methods we can use to do the structure analysis, specifically finite element analysis. Some of you might have taken the EMCH 308 course in which you used a different finite element analysis based software, Abacus. But in this lab, we are going to learn about ANSYS. We are also going to review the key concepts of stress, strain, and deformation. We will learn about ANSYS workflow, and we will discuss what to expect in the lab. This lecture is going to be a very short lecture because I'm just here to introduce what is going to happen in the lab. You want to focus more on the lab recording itself, in which I will take you through all of the steps you need to take to do the lab, and then finalize and submit the worksheet for this specific lab. Okay. The first question you want to answer is, what is a structure analysis? The structure analysis essentially is a method to predict how structures behave when forces are applied. We do use the structure analysis to find out whether a bridge, for example, can support the weight of a traffic, or how much will an airplane wing bend during flight, or where will a beam break under too much load. So the idea of a numerical structure analysis is to replace building and testing every design by numerically designing it and simulating it, which is going to be very, very cheap, specifically with the current tools that some of them are actually given to us for free. We can actually use all of these for free. So a very important part of being an engineer is to learn how to do computational design and analysis and testing. Our focus today is, of course, on structural design. Next week, we are going to focus on fluid dynamics, and we will discuss CFD for the next lab. A couple of different concepts that we need to be familiar with. Again, I'm sure you have seen this many, many times throughout your courses. And this will not be the last time you will see these introductions, but it is always not a bad idea to review. In a structure analysis, we have two very important parameters. One is stress, which is force divided by area. The units of stress is pascals or newtons per square meters. And essentially the idea of it is we want to measure how hard is the material being pushed or pulled per unit area. Again, force per unit area. We are essentially looking at a specific points where the force is being exerted on. The other important parameter is called strain. A strain is defined as change of length divided by the original length. Of course, it is dimensionless, it doesn't have any units, and we want to standardize the amount of deformation a material experiences based on an applied load with this specific concept. Okay. And deformation, of course, is a bit more general compared to a strain. Deformation is the change in shape or size of an object when you apply force. We have two different types of deformation. We have elastic deformation, which happens when the object returns to its original shape when the force is removed. And the other is plastic deformation, when the object stays permanently deformed. In this lab, we are going to focus on elastic deformation analysis. So this is the simplest type of analysis, a structural analysis we can do in ANSYS or any other numerical software. The method ANSYS uses and a lot of structural analysis softwares use is called finite element analysis. The idea of the finite element analysis is that we are going to break a very complicated structures into a small elements and then solve the equations for each element separately, and then we're going to combine the results to find the results for the whole structure, complicated structure. The idea, again, the simplified version of the idea, an example, an analogy for it is for us to, when you place a thermometer in each part of a room and then combine the results of temperature readings for each part of the room, each essentially location in a room, into one huge heat map, for example, to represent the temperature distribution in a room. Again, the idea is we break our structure into small pieces, solve the equations for that specific piece, and then combine all of the results together. Like, this is a somewhat complicated process, but as far as you are concerned, you only see the outputs of it in ANSYS. You don't really have to write the equations. You don't have to find the relationship between these different pieces. You only need to learn how to use ANSYS to use this method, right? And in the steps of FEA analysis is, first of all, is also the first part is to break your structure into smaller pieces, meshing. This process is called meshing. We're going to divide our geometry into smaller elements. These elements can be triangles or rectangles, and this has different meanings for your equations, but as far as we are concerned, we are only concerned with stability and results at this point. We don't really care about equations in the background. And then we apply conditions. We essentially tell our software where the force is being applied, where the wall is, and what is the material that is being used in the beam, and so on and so forth. And eventually we are going to solve the problem using the exerted force and calculate the stress, strain, and deformation at every node in the mesh. Okay. The ANSYS workflow itself starts with Design Modeler. This is one of the CAD softwares that is incorporated in ANSYS. ANSYS itself has 3 different CAD softwares. The oldest one and the simplest one to work with is Design Modeler, and we've been using Design Modeler for a long time now, but there are 2 other CAD softwares included in the ANSYS package. But you can also use Creo or SolidWorks or CATIA, whatever CAD software you're comfortable with, and export your CAD model into your meshing software directly. So after Design Model, after designing your geometry, we have to divide our geometry into smaller elements, which is essentially our meshing, and then we are going to use the mechanical module in ANSYS to apply our loads and boundary conditions. We're going to move on to the solver modules in which we calculate the results, and the post-processing is where we actually see the contours for stress, strain, deformation, different anything that we actually want to see. In the lab, we are going to create a cantilever beam that is 200 millimeters by 20 millimeters by 20 millimeters. We are going to fix one end of the beam and then apply a 1000 Newton downward force to the other end. So this beam essentially is can act like a wing, for example, a wing of a car. The cantilever beams are used in a lot of different locations. And eventually we want to observe how the beam bends and where the stress is the highest. And my expectation for you is to give me the maximum deformation that occurs at the free end and the maximum stress that occurs at the fixed end. Okay. What you will need to submit would be the screenshot of your CAD model from Design Modeler or any other CAD software, a screenshot of the mesh, a screenshot of total deformation contour plot, a screenshot of equivalent for Mises stress contour plot, and answer the questions we have posed to you in the worksheet. There is no need to add any extra info. Okay. As I said in the beginning, this lecture would be a very, very short lecture, and you want to focus mostly on the software tutorial, not necessarily the lectures. Thank you for listening. Please let us know if you have any questions.